So it's my pleasure to introduce the next two speakers. So let's see. So we have a shared presentation by Nidhi Seethapathi and Josephine Wang from MIT, and it's about the dissociation between temporal and spatial variability in locomotor development. The stage is yours. Let's give a warm applause for
Hey everyone. So the central question that my research group is interested in, which is shared with many of you, is understanding whether current AI models learn to move the way we do. And so we want to compare sort of behavior on learning timescales in motor development in humans to that in AI models. And so one reason this is a very fruitful question to answer is that whether the answer is yes or no, those are both interesting and valuable. So for instance, if the answer is yes, they do learn the way we do, then these AI models can serve as hypotheses for how humans learn to move on developmental timescales. And if the answer is no, then perhaps we can learn something from how humans learn to move and then inform how AI models are trained. And I would say this is a relatively open space. There hasn't been sort of a lot of work in this space, particularly in my field, which is on locomotor development. Some of the work that has been done takes what I call the data-driven approach, where they take sort of trajectories of how sort of the paths and speeds that infants exhibit when moving around in a playroom, and then train sort of simulated robots and using reinforcement learning with those same paths and speeds. And they draw conclusions from that. So some conclusions that have been drawn, for instance, is that infant-like paths and speeds help robots sort of learn to perform better in tasks like soccer, so these soccer bots, or also infant-like high error tolerances, like infants are much more okay with falling down than most robots are, help these robots sort of learn more generalizable policies that are also performant. And so today we're going to try to take a slightly different approach, which I call the predictive approach, where instead of sort of training on data, we choose some sort of canonical behavioral pattern, and then we characterize that in humans on developmental timescales, and then also in robots on learning timescales, and then we compare them to each other, and then we draw some conclusions. And so coming to the baby observe sort of session, right? We really wanted to pick some behavioral feature that is very canonical and classical. And one example of this in locomotion is this relationship between the speed at which we walk and our stepping patterns, specifically our step length and our step frequency. It's been known for many decades now that there is a very sort of strong relationship between these two in adult humans and actually across a lot of species as well. And there have been very few studies in the literature exploring this on developmental timescales quite a few years ago. Notably are in the 60s and in the 90s, the two that are featured here. And in particular, what these studies were not able to do is actually characterize these patterns within individual. So they're usually pooled across individuals, and we know there's a lot of inter-individual variability on developmental timescales, and so it's particularly important to characterize this relationship within an individual for comparing to AI models, because AI models also exhibit a lot of inter-individual variability because of the seed dependence in reinforcement learning. And so for this reason, that is the particular behavioral observation that we went after here that Josephine will now tell us more about.
Yeah, thank you. So to collect movement data from children, we use the Vicon motion capture system. And Vicon uses a multi-camera system to detect retroreflective markers placed on the child's body. On the photo on the right, we can see that markers are placed on the pelvis, the thighs, the knees, and the heels. And we have 8 cameras located around the room to reconstruct the 3D digital skeleton of the child. So in this case, we only care about the legs because we're tracking gait. We collected data from 19 children, ages 9 to 45 months, and each child yielded a different amount of data points. We consider a data point to be a single stride taken while walking or running. And one difference about this approach is we were able to collect more data points per child, which allowed for a richer data set for individual level analysis. So how did we extract the gait metrics that we wanted from the 3D digital skeleton? Well, one thing to consider is that the child isn't always moving. So sometimes they're sitting or they're doing other toddler activities. And to only keep the data that we want, we set a speed threshold of 0.2 meters per second to filter out the sections where the child isn't moving. Then for locomotion, we track the z-axis of the right and left heel, and locomotion produces a sort of wave shape from the up and down motion of the feet, where the troughs of the wave are the heel strikes when the foot contacts with the ground. So we defined the time to complete a single stride as the distance between the right heel strikes, converted from frames to seconds. Then the stride frequency was the inverse of that time. The stride length was the distance covered by a single stride, and the speed was the stride length over the time to complete a stride. And we regularized all of these values by the child's height to minimize the variability amongst multiple children. So analyzing the relationship between these gait metrics, we found that children exhibited a dissociation between their spatial and temporal relationship relative to adults. So for the children and adults, we plotted the stride length versus speed and stride frequency versus speed, where stride length was considered the spatial metric and frequency the temporal metric. And our findings show that children exhibit an adult level of spatial coordination, showing that they have the spatial awareness necessary to coordinate how, the step length with how fast they want to move. On the other hand, for the temporal metric, we see that the relationship is less correlated compared to adults, possibly suggesting that children have not fully yet developed their temporal coordination. So to demonstrate that this dissociation isn't just due to variability amongst the multiple individuals, we plot the individual level analytics. So here we have the R-squared values for the temporal relationship and the spatial relationship. And consistently across all the individuals, we see that the temporal relationship has a lower R-squared value. So what does this say about AI? Do current humanoid models of walking represent human development and behavior? A current model of humanoid walking uses reinforcement learning, where an agent in an environment maximizes the reward function. So for a vanilla RL agent, a reward function for walking could be to track forward velocity, while also keeping the torso above a certain height. And this is to prevent the model from falling or crawling on the ground. And then we also have a negative reward for the sum of the square of joint torques to conserve energy. And this is to prevent the model from doing something like kicking off the ground and jumping super far. And so prior research, actually let me show the video to see what this reward function would result in. Yes, so we see from the video that the agent doesn't behave like a human. And prior research has shown that children don't have a strong aversion to falls, while in RL agents, part of the whole goal of the reward function is to avoid falling. So to also add to this analysis of whether RL agents align with human behavior, we also track the gait metrics of this RL agent to see whether it aligns with what we observe in children and adults. So for the training period, we segment this training period into two phases, the early phase and the well-trained phase. In the early phase, the reward per episode is increasing exponentially, which we define as the developmental period, or the period that's similar to a child. And then once the reward plateaus, in the well-trained phase, we identify this as the model having mature gait similar to an adult. So plotting the same relationships in these vanilla RL agents, we see that the models don't exhibit a human-like behavior. So in the early trained model, the correlation for the spatial and temporal relationships are pretty similar with a slightly higher variability in the stride frequency. However, as training progresses, the relationship between the stride frequency and speed actually weakens, which is the opposite of what we observe in adults. So in a well-trained model, the agent actually does not have a strong contribution from stride frequency to their walking speed. And overall, this shows that through this aspect, the RL agents aren't a representative of human development.
So this model is obviously quite preliminary at this stage, but what it tells us already is that these vanilla models are not enough to capture these patterns that we're seeing in human motor development. So the next question that we're after with this work is what assumptions could yield baby-like or human motor development like spatial temporal dissociation pattern in deep reinforcement learning. And so it turns out that once we started brainstorming, there are a lot of hypotheses that we could try to incorporate into the model. So for instance, one thing that babies do that these models don't do right now is they first learn to stand before they learn to walk. And perhaps this is actually one reason why infants have sort of a higher error tolerance, is because they have a lot of confidence in their postural control already because they've already learned to stand. And so can we now train these RL models to first learn to stand and then learn to walk? And would that automatically have this pattern emerge or this dissociation emerge? Or perhaps we have to take inspiration from neuroscience, where we know that things like central pattern generators underlie rhythmic aspects of locomotion, whereas reflexes contribute more to spatial aspects like corrections or like error corrections. And do we need to incorporate those into the model? A third hypothesis could be one, I saw this at a poster yesterday as well, is somehow maybe having more variability in the temporal pattern is well adapted to having a growing or a changing body. And so we could change the body of the agent on learning timescales and see if that is useful. And finally, it might end up being something quite abstract and mathematical, like just having different steepness of the cost functions for temporal versus spatial parameters. And so the main takeaways of this work is that the dissociation between spatial and temporal coordination exists in locomotor development, and that this dissociation holds at a within individual level. And inspired by this observation, we would like to now build deep reinforcement learning models that can recapitulate this, because vanilla deep reinforcement learning models do not seem to capture this phenomenon. Thank you.
Thanks for sharing that exciting research. And we have a question here in the middle.
Okay.
Okay. No. Oh. Okay.
Okay. I'll start. Thank you for your talk. I had a question about falling and how you may incorporate that in your model. And I mean, there's some work suggesting, I think Ori Azmi has been involved in that work, that falling is not that important in terms of penalties, but it may be important later. So I was just curious about, with your observations of the children, what you saw, but also how you might incorporate that into your model, and may that vary with the age of the child?
So we are interested in sort of understanding how humans in general, not just sort of infants, represent stability and compute stability. This is obviously just an educated guess at this point in time, but based on sort of we've built models that sort of change how stability is represented. And based on what we know, I'm actually pretty confident that this particular dissociation that we're finding is not explained by stability. I think it's likely explained by something more representational, having different representations for the temporal component and the spatial component, or having different neural underpinnings for the two of them. So I don't think this particular dissociation has a lot to do with falls.
Okay, another question? Yes, okay.
Thank you so much for the presentation. What I would like to ask is that why you have used the sum of torques as a reward function in your RL module? Because when we're trying to compare to humans and to make a claim that says the RL does not take the same way as human learning, does human learning to walk is actually modeled by the sum of torques of our joints? So that's why I wasn't quite sure the reason for the selection of that particular reward function rather than zero moment point, etc., or something else.
Yeah, so in fact, so my training is actually in the metabolic cost of walking and how it predicts sort of human walking patterns and so on. And it turns out that human metabolic costs are well approximated by the sum of the square of muscle forces. So, you know, one next step, and the sum of squares of muscle forces are pretty correlated with the sum of squares of joint torques. But one good next step for us could be to test this in a musculoskeletal model. It's actually pretty straightforward now to train a musculoskeletal model also to walk. So that could be sort of one way to answer your question.
Thank you so much for the answer.
So thanks again, and I fear that we don't have time for more questions, so please continue the discussion in the next break.